Hi, welcome to our lecture for Chapter 1 on motion. In this first part of the lecture, we'll learn how to graph motion and also learn about velocity or speed. So Chapter is broken up into 4 parts. In this first part of the video, we'll learn how to graph motion and we'll learn about the concepts of speed or velocity. In Part 2 of this lecture, we'll learn about acceleration. In Part 3, we'll talk about falling objects. And in Part 4, we will cover circular motion and centripetal acceleration. So this first chapter is about something called kinematics, which is the study and mathematics of motion. In order to do this, we're only going to require 2 units. Remember that you learned about units in Chapter 2. So we need a unit for distance, and we are going to use the meter, which is abbreviated M. And this is a meter stick. You can kind of get the idea of the length of a meter here compared to a human. And to measure time, we are going to use the units of seconds. The unit second is abbreviated with an S. By the way, distance is abbreviated with a D, and time will be abbreviated with the letter T. So we use these abbreviations or symbols just to shorten the notation, so we don't have to write out the words every time we need them. So let's start our study of motion by learning how to graph motion. And this is a very useful tool to learn and understand the concepts of motion. So what we're going to do here is take an example of a little ladybug shown here, and we're going to have this ladybug just walk across the room basically. So on the floor of the room, we have labeled the distance in meters. So the origin where the ladybug starts is labeled 0 meters. And then you can imagine 1 meter away is right here, and 2 meters here, 3, 4, 5, 6, and 7 meters. So this whole, by the way, this is called a coordinate axis. This whole coordinate axis here has a length of 7 meters, which would be about the size of our classroom if we were in the classroom. So what we're going to do here is have the ladybug act out this motion here. She's going to walk slowly for 15 seconds. She's going to stop for 10 seconds, and then she's going to walk quickly for 10 seconds, and we're going to record on every 5-second interval here, we're going to record her position here. So let's go ahead and get started with our ladybug moving. So here she's moving along the coordinate axis. You can see in the first 5 seconds she has traveled 1 meter. After 10 seconds she's traveled 2 meters. And after 15 seconds she reaches 3 meters, but now she's just going to stop. She's just going to sit there for a total of 10 seconds. But once we get to 25 seconds, now she starts moving faster. I'm trying to make her move a little more evenly. Here we go. And finally, once we get to 35 seconds, she is done. Okay, so let's take the data that we plotted here or collected for our ladybug, and let's make a graph. So this is the data table again. You can see that, for example, at time 0 seconds, remember the ladybug started at 0 at the origin, so her distance that she traveled was 0. After 5 seconds, she had traveled 1 meter. After 10 seconds, 2 meters, and so forth. So let's go ahead and plot these points on a distance versus time graph. So we have distance plotted here in the vertical axis. So notice this is a little different. You know, the ladybug was walking horizontally, but we're going to plot her position in the vertical axis. This is the dependent axis, and we're going to plot time down here, which is usually plotted on the independent axis. So notice that time is listed here in intervals of 5 seconds, and our distance is plotted in intervals of 1 meter. So we can take these points here. You can see the first point, 0, 0. Of course, that corresponds to this point on the graph right here. At 5 seconds, she's at 1 meter. So here's 5 seconds down here. That corresponds to 1 meter. So that's this point here. After 10 seconds, you can see her position in the table is 2 meters. That's right here. After 15 seconds, she's at 3 meters. Now, notice what happened. Remember when she got to 3 meters, she sat there for a total of 10 seconds. So after 20 seconds, she's still at the same 3 meter point. And at 25 seconds, she's also still at the same 3 meter point. But this is when she started moving more quickly. And she went basically the last 10 seconds, she went from 3 meters all the way to 7 meters like this. Okay, so this is, and then what we can do here is, our blue points here represent the data in the graph, and since she was moving in sort of a continuous fashion, at least I tried to make her move continuously, we can connect these dots just with a straight line like this, and this plot now represents, this is the graphical representation of the ladybug's motion. So we're going to use this graph and interpret it various ways, as will become more clear soon. So what we just described with the ladybug was one way to describe her motion, of course, was her position versus time. But we can do more than that. We can also describe the ladybug's velocity or speed. So what do we mean by speed or velocity? It's a measure of how fast an object travels. More specifically, it's the change in distance per unit time. Now, in this class, we're going to use the term velocity and speed to mean the same thing. In more advanced classes, you'll learn, that velocity is actually a vector that has a direction and a magnitude to it. But in this class, in GES 100, we're just going to, we'll use the word velocity and speed to mean the same thing, basically how fast something travels. So to calculate velocity, so V for velocity, it's pretty simple. We just take the distance that the object traveled in meters and divide it by how long it took to travel in seconds. So it's distance over time. So we can see that the units of speed are meters up here divided by seconds down here. So we say meters per second, all right? And we can write that as meters / second, or we can abbreviate it, which we will do, as m/s. So m/s means meters per second. So the meaning of velocity, let's just take an example here. Here's our dog running along. Let's say this dog is running with a velocity of 5 meters per second. Well, what does that mean? It means the dog runs 5 meters per second. In other words, each second of time, the dog runs 5 meters. So using our definition of velocity, we can now solve 3 different types of problems. So these are what we call word problems that are associated with speed or velocity. So let's look at number 1 here. A student walks 120 meters in 1 minute. What is her average speed? All right, so here she is walking along, covering 120 meters in 1 minute. Well, we know that velocity or speed is distance over time, so the distance is certainly 120 meters, but remember the time here we need to measure in seconds, not in minutes. So we just convert 1 minute is, of course, 60 seconds. So 120 divided by 60, that's 2. We can do that in our head. So her average speed is 2 meters per second. All right, so she's covering a distance of 2 meters every second that she walks. So question number 2 is, how far would this same student walk in 35 seconds? So we know that velocity is distance over time. We need to solve this equation for the distance because we're trying to figure out how far she would go walking at this speed for 35 seconds. So we need to solve V equals d over t for distance. So the way to do this is we need the d to be all by itself, so we can multiply both sides by t. Notice what happens when we do that. Over on the right side, we get distance over time, but we multiplied by t. As long as we do it to both sides, of course, we can do that. These t's now cancel, and we have vt on the left is equal to d all by itself. So we have solved for d. So d is equal to vt. I can write it in the opposite or reverse order here. And now let's fill in the numbers. What do we know? Well, the student, we know the same student is walking at 2 meters per second. That's v. And the time that we're interested in is 35 seconds. So again, we can do this in our head. 2 times 35 is 70. And notice what happens here. We have meters per second times seconds. These s's cancel, and we're left with just the m for meters. And that makes sense because obviously we're solving here for a distance, so the distance ought to be in meters. The third question is, how long would it take the student to walk 1,000 meters? So again, if we use v equals d over t, now we need to solve for time because we're trying to figure out how long. So the first thing we can do, there's a couple steps here. We can, again, multiply through by t to get vt equals d. And then to solve for t, we need to divide by v. So divide both sides by v, and we have time is equal to distance divided by velocity. So we have 1,000 meters is the distance she walks, and again, her velocity is 2 meters per second. So once again, we can do this in our head. 1,000 divided by 2 is 500, and here we have meters over meters, so the m's cancel, and down here we have 1 over seconds, but since that's in the denominator, that actually comes up to the top. So this s returns to the top here, and we end up with 500 seconds for our time. Let's go back to our graph for the ladybug that was walking, and let's see what we can make sense of this graph in terms of the velocity or the speed of the ladybug. So remember, the ladybug had sort of 3 different parts to her motion. The first part, she walked at a slow pace until she got to 3 meters. Then she stood still, and then she walked quickly. So let's just look at the first 15 seconds, and let's see if we can calculate how fast the ladybug was walking during those 15 seconds. So we know that velocity is equal to distance over time. So on this graph, notice that her distance, she starts at 0 and she walks to 3 meters. So this is the distance that she walked right here. Now, on a graph, this is how far this line here rose up. This is called the rise of the graph. And underneath here, remember, we have to divide by the time it took to walk those 3 meters. That's this portion here, the 15 seconds, and this is called the run of the graph. So we see that velocity is equal to the rise over the run of the curve that, or the path on the graph. And you'll remember from math class that rise over run tells us the slope. So this is sort of an important result. The speed or velocity of an object is equal to the slope on the distance versus time graph. So we can now plug in our numbers, of course. The distance during this portion of the graph right here was 3 meters, shown here, and the time was 15 seconds. So 3 divided by 15, you can do that on your calculator, or you'll notice that that's 1/5, which is 0.2 meters per second. So, notice that's a pretty slow pace, right? She's only covering 1/5 of a meter every second. Let's go ahead and analyze the velocity of the ladybug for the other portions of this graph. So remember, the next 10 seconds, what was the ladybug doing? Well, she was standing still. So notice the graph here. If we take, her velocity is the distance traveled during this portion right here that's circled. And of course, that's 0, right? She didn't move. There was no distance traveled at all. The rise of the graph here is 0. And the time, that she was standing still was 10 seconds. But of course, 0 divided by anything is 0. So this tells us here that the velocity of the ladybug right here is 0. That makes sense, of course, she's standing still. More importantly, from the graph, notice the slope of the graph here is 0, right? This portion of the line here, this line segment, has no slope at all. It's horizontal, it's flat, meaning no speed or velocity. And then during the last portion of the graph, when the ladybug started moving again, let's calculate her velocity there. Well, it's the distance traveled divided by the time it took. Now here we have to be careful. The distance that she traveled during this portion is not 7, it's 4. Now how did I get that? Well, she started at 3 meters right here, and she moved to 7 meters here. So 7 minus 3 is 4 meters. That was the total distance traveled. And then the time, we also have to be careful there. The time here is not 35 seconds. The time is 10 seconds because we're starting here at 25 seconds and ending here at 35 seconds. That is a total time of 10 seconds. So her velocity during this steep portion of the graph here is 4 meters over 10 seconds, which is 0.4 meters per second. So using the concepts that we just learned about velocity being equal to the slope of the graph, we can look at a graph like this and figure out who's running fastest and who's running slowest without having to do any math at all. So look at this graph. This is another distance versus time graph for 3 different objects. Again, these could be 3 different ladybugs or 3 different people, turtles, it doesn't matter. Object A has this curve here. Object B has this blue curve here, and object C is the green curve here. So who is running the fastest between these 3 objects, A, B, or C? Go ahead and pause the video and see if you can figure this out. Okay, so the answer is B. Remember that velocity or speed is equal to the slope of the graph. And the blue curve here is the steepest line, which means the fastest speed. So now we can also quickly figure out who is moving the slowest here. Who did you think? Well, the answer there is A. The reason is A has the least amount of slope in the graph. Okay, if you think of it like a hill, right? This is the least steep hill. So A goes the slowest. So on our last slide here in this part of the lecture, we can sort of extend our conceptual analysis or interpretation of motion graphs. Let's look at this same graph here that we just did on the last slide for object A, B, and C, and let's ask a bunch of questions. For each of these questions, why don't you pause the video and answer them, and then we'll check to make sure you got it right, which will tell you that you are doing well in understanding how to interpret motion graphs. So the first question is, where does object A start? So go ahead and pause the video. All right, well, from the graph here, we can see that object A starts right here, which is at 4 meters. Question number 2, where does object B start? So again, pause the video and figure this one out. All right, so object B starts here, but notice that's at 0 meters, okay? So the answer to question number 2 is 0 meters. Number 3, when does object B start moving? Well, that is right here, and now we're going to read down here on the time axis. Object B starts moving at 15 seconds. So what does that mean? Well, that means that if the clock starts here at 0, object B just waits 15 seconds and then starts moving. Question number 4, which object is moving fastest? Well, we already answered that one. Remember, it was B because of the steep slope. Which object is moving slowest? We answered that one also. That was A, because it has the least slope. How about question number 6. Which object traveled the farthest? Again, pause the video and see if you can figure this out. All right, so the object that traveled the farthest was actually object C. Object C traveled 4 meters because it started at 0 and it ended at 4. Now, if you said object A, well, that's incorrect because object A started at 4 meters and ended at 7. So object A only traveled 3 meters. Same with object B. It went from 0 to 3 meters, which is a total of 3 meters. So object C traveled the furthest. Okay, so that is the end of this first part of the video lecture from chapter 3. I will see you shortly in part 2. Goodbye.